Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in here we're going to explore binding energies and how this is related to atoms, and when you have a specific atom and this atom we want to split it, with the masses be the same before and after. And we could also look at other things involving how to determine the mass defect, and also leading us into different ways to determine the binding energy. So before we dive into this, please don't forget to hit the like, by the way others can actually get a chance to check out these videos, and also subscribe, so that of course subscribing is free. So let's begin by actually looking at this particular question, which says that we should calculate the binding energies by nucleons for iron 56. And take note, we have to use atomic masses for all the particles that are present in here. So first off, let's look at various identifying variables that we need to take into consideration concerning iron 56. So we know, of course, that to represent various atoms or elements, we actually have our A value, which is as a superscript, and then the Z value, which is our subscript. We know that Z value is actually known to be called the atomic number, and the atomic number actually gives us the number of protons that are present in there, and also is equal to the number of electrons. And on the other side, A is known to be called the atomic mass, and the atomic mass is not a whole number. It accounts for the different isotopes relative abundance in or for that specific element. So in this case here, since we have iron, we are going to consider this to be not a whole number but a decimal, and you can find this number on the periodic table. So let's move on into how this translates into iron. And so iron, what we realize is that the atomic mass of iron here is around 55 point, in this case looking at 55.845, and while the atomic number in this case is 26. So what does that mean? It means that 26 is the total number of protons, and then the number total of electrons as well. And in this other case here, we know that since we're considering the isotope of iron 56 to be our specific nucleon, then we assume that the number of neutrons in this particular element here is going to be determined by taking away our specific number of protons from the atomic mass. But in this case here, we're going to use the mass number. So this is equal to the mass number, I'm going to represent that Mn, minus the number of protons. So therefore our neutron number number is in this case equal to 30. So in this part here, we were able to determine what the number of electrons are, the number of protons are, and the number of neutrons are. So what are the things that actually makes binding energy actually be established in the first place? So we know that for sure our Ma, which we're going to represent here as our nucleon or nuclear mass, is not equal, surprisingly, or I would say not surprisingly, to the number of protons plus the number of neutrons. And why is this the case? Because when we actually discover that, or we actually determine the mass of when the atom holds all the particles in that place, like for example, let's say we have 2 protons, and then we have 2 neutrons, and then we have our 2 electrons. We're going to represent as, let's say, X here, and this is actually found in an atom, and you determine the mass when you actually fully take apart all the particles without any form of attraction or maybe repulsion present in there. In this case, we've taken all these particles out fully without any form of attraction or repulsion, and then you actually determine the masses for each particles on the right side. We actually found that the mass combined on the right side, which we're going to represent as mt, is not equal to the mass of that particular atom or nuclear mass right here on the left side. And so why is that the case? When you look at it here, we consider this to actually be due to the fact that the mass that is needed to have the left side to be equal to the right side is represented as a form of energy. And so this energy here is known to be called the binding energy. And so our binding energy is represented as mass differences that will enable us to determine what the energy is required to get to our specific individual particles when they are fully separated out right there. So how are we going to actually apply this to energy? We know that the difference in mass in this case here is going to get us to our binding energy, which is represented as the change in energy. But first, what is change in mass? So how are we going to determine a change in mass? Our change in mass, or I will call it the mass difference, is actually equal to our specific unit for mass difference to be kilograms per mole. And so once kilograms per mole is our unit for the mass difference, then we know that in order for we to determine the mass difference, we are going to relate our total mass with that of our atomic mass or our nuclear mass in here. So in here, to determine that, what we have to do is move this to the other side, and in that case we know that the mass total is going to be minus our mass atomic, so the whole atom mass, that is when they are together. So hey, you know what, our change in energy is similar to our specific mass difference multiplied by our speed of light square, which is reminiscent to what we know from Albert Einstein's theory of mass equivalence to energy, and how that actually led to the theory of the Big Bang, where energy was required to create mass, and so no energy is lost, or no form of particles is gained or lost. Everything is all contained in the system. And so our goal now is to be able to determine what our mt is and what is our ma. So for our ma, we know that our ma, we're going to mainly use in this case our atomic masses. So in this part here, we're going to use the one that we found on the periodic table, but in this case iron, which is going to be 55.8, get the number right, 45 U. However, for our mass total here, we're going to need the number of protons, mass, atomic mass unit, the number of neutrons, atomic mass unit, and that of the electrons. I know, of course, the electron is not significant in terms of the mass, but we're going to include electrons into consideration. Some examples will exclude electrons. I'm going to use electrons because, I mean, we want to get the accurate value. You know, if you can use the smallest or the least, weight considered in this particular example. So in here, let's start off with our specific example, which involves first determining our total particles when they are fully separated, and we want to determine the atomic mass unit for each particles in there. So in here, first, we know that Z is the atomic number, and this here is going to be multiplied by the proton mass, and then we add it to our nucleon, I keep misplacing that, neutron number, which is represented as N, multiplied by our neutron mass, and then we have our total electrons multiplied by the mass of our electron. So this here is going to be equal to our atomic number of our specific proton. In this case is 26, multiplied by our specific atomic mass unit for a proton, which is in this case 1.00, in this case 7276 U. And so our next one here is for our neutron, and if our neutron, we have 30 of them, and this is going to be multiplied by 1.008664 U. And finally, for our electrons, we know that we have 26 of them, and this is multiplied by 0.000548 U. So take note that this number here that we've determined is actually gotten from a table, or you can go on the internet and type what is the atomic mass unit of a proton, a neutron, and an electron, and you're going to get those numbers out there. So you don't need to actually determine the number of the cuff. We don't expect you to memorize these numbers, but you know, maybe some other areas around the world you will have to memorize the numbers, but in this case you don't really need to. So once we have this taken care of, we're going to add all these numbers after summing the products of each of them together, and we're going to get our mass total when they are fully separated out. And so what we have here is going to be 56.4633596 atomic mass unit. So this number here, MT, is actually equal to this number when the particles are fully taken out of our particular atom. And we are now going to determine the other variable, which is MA, which is our atomic mass unit of our iron. So we know, of course, that our atomic mass unit of our iron here, which is represented as MA, is equal to 55.845 U. These here will be subtracted from each other for we to determine our mass difference, which is represented as M changing M, which is right here. So once we have this taken care of, we know that our M changing M is equal to around 0.61836 U. We just got to only consider that as our number for our changing M. So what does this imply here? This implies that our U, looking at it closely, is actually represented as grams per mole. And since it's represented as grams per mole, we want to convert this to kilograms per mole so we can use it in our energy conversion. So to go from grams to kilograms, we need to, in this case, divide by 1,000. So our changing mass is going to be 0.61836 U, well, in this case grams per mole, times, take note, we're multiplying this by 1 kilogram over 1,000 grams. And so therefore, once this cancels this, what we have using or representing this as our specific scientific notation is going to be 6.1836 times 10 to the negative 4, in this case kilograms per mole. So take note here that we'll need this particular mass to determine our energy, which is our changing energy. So there are two ways to go about it. I know it's always two ways to go about solutions like this. Now, one way is involving determining the joules per mole, and the other way is by using the mega electron volts. And so one way is, well, let's clarify this by actually changing the color to make things stick out. And so in here, we're going to determine our joules per mole. And to do that, we are going to be using our change in energy to be equal to our change in mass multiplied by our speed of light squared. That is one way. Now, the other way here is by using another different formula, but it's closely related, which is equal to change in E is equal to change in M multiplied by 9. Don't forget this number, 31.494 mega electron volts per mole. So this is the other pathway that leads to mega electron volts per mole. And you got to see some of the conveniences and the setbacks of both of them so that you can have an idea of what we are actually dealing with in this particular example. So when we begin here by looking at the left side, and we are doing the change in energy is equal to the change in mass multiplied by the speed of light. We know that in this case, our change in energy is going to be our mass difference, which is 6.1836 times 10 to the negative 4 kilograms per mole. And so this is multiplied, take note, by the speed of light 3 times 10 to the 8 squared. And we know that the unit, since it's squared, is going to be meter per second all squared. So therefore, once we have this expressed, we are going to be able to determine our energy in this case, and take note that the energy is going to be represented in joules per mole. So therefore, in this part, we have our energy to become 5.5652 times 10 to the 13 joules per mole. And so once we're able to do this, just that, we can actually convert our joules per mole to mega electron volts. But you know what? Let's go to the mega electron volts and let's see our answer first for this particular pathway. So for this pathway, we know that our change in energy is equal to our change in mass, which is 6.1836 times 10 to the negative 4, in this case kilograms per mole, times, in this case here we have 931.494 mega electron volts atomic mass unit. So the denominator of our unit, take note, is represented as our U. And so in this case, we can now conveniently deal with our units and everything involved here. So it's really important to be able to actually catch various unit conversions and use the unit to your advantage in realizing whether you're on the right track or you need to go back and clarify your solution. So therefore, in this case here, our change in energy using this method here is actually going to be equal to 575.998 mega electron volts. So since you have this as your value for our change in energy, that is really interesting because you're wondering, how is this on the left side equal to that on the right side? Because of course one is mega electron volts and the other is in joule per mole. The cool thing about this is that you can actually convert these to mega electron volts. What we know is that 1 mega electron volts is equal to 1.6022 times 10 to the negative 13 joules. So therefore, our change in energy using this method is that we'll have to perform an operation with our specific two numbers. And so to determine that, we have to actually, in this case, divide our joules per mole by our specific mega electron volts with respect to joules. And so in this case, we're going to be multiplying by 1 mega electron volt over 1.6022 times 10 to the 13 joules. So therefore our joules cancels out, and what we have now is 1 multiplied by our numerator on the other side, and we are going to actually get our change in energy to be equal to, in this case, 3.4735 times 10 to the 26 mega electron volts per mole. And so you're wondering, oh, it's per mole, but still it's not equal to the one at the right side here. So how is it possible to actually get our number to be equal or closely equal to this number right here? So what we have to do now is we would then have to change our mole to number of particles. So therefore in here we know that the Avogadro's constant is a good way to indicate that, where 1 mole is equal to 6.02 times 10 to the 23 particles of iron. So therefore once we have this actually taken care of, we are going to get our number that is really close to our value, which in this case here is going to be equal to change in energy to be equal to 576.99 mega electron volts. So this is amazing because we have almost the same values from here and in here, comparing our two methods. So no method is right or wrong, as long as you're able to see how we can go from one equivalence to another and see the bigger picture, that what matters in this particular case. So once you have this, you're wondering, is that the right answer, or is that our final answer? Are we good to go? No, not really, because the question actually says per nucleon, which means that we are considering these specific particles right here. So if we assume that we are dealing with this particular isotope of iron, what will be the energy that we release per nucleon? So therefore in this case, all we have to do is actually divide our specific energy by 6.99 mega electron volts by 56 particles, while considering mainly the proton and the neutron in the nucleus. So per nucleus, not including the electrons, what energy will be released in this process? And so in here we're going to have our number to be roughly around 8.790 mega electron volts. But if you check a calculator using that same number, we are going to have actually we have 10.30 roughly. So it's going to be between around 8.790 to around 10.303 mega electron volts. So this number here is truly coming from this particular method, and why this number is gotten from the other method that we actually took care of on the other side here. Moving up, let's get this continued over there. So that is about it for this particular long video. I hope you're able to understand how to actually go, from our specific individual particle masses when they are together to when they are fully separated out, and realizing that, hey, you need a specific binding energy in order for you to accomplish total energy particles when they are fully separated out. And once you're able to do that, you need to be able to recognize the conversion units and number of particles when given the symbols of elements, and from there you'll be able to determine the mass difference, which is actually going to be taking away our specific atomic mass unit of that whole particle when they are together, atom, to that when to that of the separated number of particles, which includes, in my own example, number of electrons. And so to accomplish that, we need to multiply our number of particles that are of the same charge with its mass. In this case, we have protons, we have our neutrons, and we have our electrons. And in the total particles, when they are fully separated out and taking away our atomic mass unit from the total particles, will enable us to find the mass defect or the mass difference. And so take note that we got to change our mass difference, because it's from U, which is equal to gram per mole, to kilogram per mole. And then once you have this method taken care of, we can then either use two ways of actually solving our problem, either using mega electron volts or using our specific meter per second. So therefore we can get the joules per mole, and then you can also convert joules per mole to mega electron volts, and then we can actually determine for a nucleon, which is inside the nucleus, considering the number of particles for that particular type of isotope. So that's about it for this particular video. I hope you have found this really informative. Hit the comment down below, let me hear your thoughts about this, and also don't forget to subscribe. By that way I can catch you later, and also others. Of course, subscribing is free, and also hit the like. By that way others can actually have the chance to check out these videos. All the same, stay smart as always and believe in yourselves.